Okay, good morning, everyone.
Good morning, sir.
Good morning, sir.
I guess you can see
Good
my
morning,
screen.
Yes, sir.
Okay. So we were discussing about Bessel equations. So there's another interesting case is when p equals to half. When p equals to half. So in this case, the Bessel equation becomes y double prime plus x into y prime plus x square minus p square, that is going to be 1 by 4. X square minus 1 by 4 to y is to 0. Okay, so in this equation, if I substitute y equals to sum ck x power k plus r. Sorry, this is x square y double prime, right? X square y double.
Yes.
Okay. So when we substitute this, differentiate this and write in the equation, we get the Ly. So let me write this as L. Ly becomes the sum k plus r into k plus r minus 1, okay, times x power k plus r, right? X power k plus r into ck. And the second term will have the k plus r into ck, right? And also this minus 1 by 4 into y will have minus 1 by 4 into ck. So this is this comes with x power k plus r, and the another sum is x square y. So x square y is going to be ck into x power k plus r plus 2. Okay, so this is this tells me that now I can write the for k equals to 0 and right. So this first thing is that to transform this sum into the form of that. So I write k plus 2 equals to k, or replace k by k minus 2. So this becomes k equals to 2 to infinity. So I'm replacing k by k minus 2. It becomes ck minus 2 into x power k plus r. Okay. So since this is starting with k equals to 2, so from this sum I should take out the k equals to 0 and k equals to 1. So if I do that, the k equals to 0, the k equals to 0 if I put, I get r into r minus 1, okay, and plus r into minus 1 by 4 into k into ck. So this is c naught plus k equals to 1 is going to be, this is r plus 1 into k equals to 1 gets cancelled, so you have r, and this is going to be plus 1 plus r, okay, minus 1 by 4 into k into c1, plus we have the sum k equals to 2 to infinity of k plus r into k plus r minus 1, right, plus k plus r into minus 1 by 4 to ck, plus ck minus 2. Sorry, so times ck plus ck minus 2 into x power k plus r. So this also, there is x power r here, and there is x power r plus 1. So all these things are going to be 0. So that means we get the individual polynomial, which is r into r minus 1 plus r minus 1 by 4, that is r square minus 1 by 4. So that is pr, right? R square minus 1 by 4 into C naught x power r plus this is going to be r plus 1 into, so this is going to be r plus 1, okay, r plus 1 whole square minus 1 by 4 into C1 into x power r plus 1. So these are the first two terms, and third term is this one. Okay. So this gives the roots, as we already saw, that r square equals to p square. So this r equals to minus half and plus half. So r equals to there are two, one is half and r equals to minus half. So let me write this as r1 and this is r2. Okay, so the solutions corresponding to r1, there's no problem, because p of r1 plus k is going to be non-zero, right? So p of r1 plus k is non-zero for all k, where p is the individual polynomial. Right, so therefore the first solution is not difficult to define. So from the recurrence relation here, so this becomes k plus 1, k plus r into k plus r, that is k plus r square, right? So this is k plus r square plus k plus r. So you can write this thing. What is the, that is going to be r plus k whole square minus 1 by 4. So that is, you can simplify that. You see that r plus k whole square minus 1 by 4, okay, into the ck plus ck minus 2 equals to 0. So this is true for k equals to 2, 3, 4. So this is our p of r1 plus k, p of r1 plus k. So this implies that all the coefficients ck, which is minus of ck minus 2 by upon k into k plus 1. Okay. So when you see this relation here, then I take r equals to half in this one, right? So everything has to be 0. When r equals to half, this is going to be half plus 1, that is square minus 1 by 4. This is non-zero. Therefore, C1 has to be 0. Okay, and C1 has to be 0. So C1 is 0, and these two things combinedly implies that C3, C5, all the odd coefficients are going to be 0. Therefore, you get C2m is going to be minus 1 power m into C0 by 2m plus 1 factorial. So this gives the first solution. Okay, so the first solution is x power half into, this is x power 2n. Okay, so this is first solution. So you can see that this can be written as x power minus half into sin x. So this is j half, which is what people also call it as Bessel function with some special constant, by choosing C0 as some special constant, right? C0 times this. Okay. So that special constant is when I choose that constant, we call this as, so this is 2 pi times the solution that we found, that is 1 by root x times sin x. So this is for x positive. So when I take R2, that is minus half. Okay. So in this case, what happens is since R2 minus R1, which is R1 minus right, R1 minus R2, that is half minus half is going to be 1. So that means the coefficient of C1, okay, so C1, finding the C1 is going to be an issue. Okay, so let us look at the expression that we get. So what we have here is this is anyway 0, right? So we have Ly is going to be like this. So Ly when r equals to r1, r equals to r2, Ly is going to be this 0 times x power r plus right, so C0 plus C1 times the expression is going to be r plus, right? So this is right, so this is what we have, r plus 1, right? R plus 1 square minus 1 by 4, r plus 1 whole square minus 1 by 4. So r plus 1 whole square minus 1 by 4. Right, x power r plus 1 plus the recurrence relation, right? So when I take r equals to r2, okay, so this is equals to 0 when r equals to minus of. Okay, when r equals to minus of, this becomes 0. So that means x power r plus 1 is not 0. Therefore, obviously C1 becomes 0. For the whole expression to be 0, okay, implies that C1 is 0. Automatically you are getting C1 to be 0. And we saw that only C1 has a problem. All other things are will follow. So C1 equals to 0 again implies C3 is 0 from the reconciliation, and C2k plus 1 is 0 for all k. So that means all the odd coefficients are 0 and even coefficients are governed by the reconciliation. So the even coefficients are governed by the reconciliation. So so that means that there's no I can take C3 to be 0, or I can take C1 to be 0, or I can take basically it is going to be arbitrary. So it will be arbitrary. But in particular you can take them to be 0. But when you take it to be 0, then you get already you got the first solution. So you can take them to be arbitrary coefficients and then write C2k is going to look like minus 1 power k into C0 by 2k factorial, and C2k plus 1 again depend on C1 by 2k plus 1 factorial. So when you substitute this, you get the second solution P2 as x power minus half, that is R2 times A0 cos x plus A1 sin x. Okay. So this we already saw that A1 is A1 sin x is already there. So this J half, okay, so that is the J minus half is and again a Bessel function is coming one when A1 equals to 0. So that is 2 by pi x power half into cos x, okay, x positive. So this is a Bessel function of second kind. Okay, so this is also a Bessel function. Okay, so what we saw here is that when it is when p equals to half, okay, when p equals to half, this is what is happening. But if you see the close observation from here, you see that the what this expression becomes here, right? That's what we wrote as a recurrence relation, that is r plus k whole square minus 1 by 4, right? So in case of r equals to p, what happens is p plus, right? So it's going to be k plus p whole square minus p square. So for general p, what the recurrence relation you will have is p plus k whole square minus p square, okay, times ck equals to ck minus 2 with the minus a. But this one, see that when k is, so we basically want to see when this is going to be this itself is going to be 0, right? This is going to be 0. So the case when it is going to be 0, so you expand this, you see that this is p square minus 2pk, right, when r equals to minus p. So I write this as maybe r. This is what we have. When r equals to minus p, it becomes minus p plus k whole square, right? So when r equals to minus p, this becomes right. This becomes minus p plus k whole square minus p square into ck. So that is minus. This is going to be p square, right, plus k square. What am I doing? P plus k whole square so p square plus k square minus 2pk minus p square. So p square gets cancelled and we have k minus 2. Okay, so when p equals to k by 2, this becomes 0. When p equals to k by 2, this becomes 0. So in this case, what happens is that is when k by 2 is belongs to a natural number, then no log term is required. So we can do the same thing what we did for r equals to 1 by 2. Okay, the same procedure one can do, and then find the coefficients using the recurrence relation, and there won't be any logarithm term that is required in this case. So that is when p by 2 is a positive integer. Okay, so when p by 2 is a positive integer, you can do this. When 2p is a positive integer, right? Kp equals to k by 2. K by 2 is in n. We can do this. Right? So that is when. So only thing that is left is 2p is not equals to n for any n. Okay, so this is the final case. You have any questions?
Sir, how do we get that equation for general P?
This we already have. This equation you mean?
Yes, sir.
This is a recurrence relation, right? This is what we have here. The recurrence relation. This one. R plus k whole square minus p square, right? This is p.
Okay, sir.
This is p. I took the p equals to half, therefore I got 1 by 4. Otherwise you get p square. So whenever this k by 2 is a natural number, that is, or let me say 2p is, k is a natural number anyway. So it's not what it means that 2p is equals to k, right? So this is a natural number. So for that particular integer, only you will have problem r1 minus r2. R1 minus r2 is also equals to 2p. Okay, so the 2p equals to k, you have that problem will not be there because this itself becomes 0. Therefore, all the coefficients can be calculated using the recurrence relation. Okay, so the only case that is left out is when 2p is not equals to n. Okay, so when 2p is not equals to n, you can just write the series and then substitute. So these find the solution. So you will find the first solution as jp, that is when r equals to p. Okay, for this one, you will find that using the one can use the recurrence relation to see that c1 equals to 0 and all the ck2 plus 1 is going to be 0 for all k. So therefore, you get the C2m is going to become minus 1 power m into C naught by 2 power 2m into factorial m into p plus 1 to p plus 2. This all just comes from the same calculations what we did for finding the solutions. So these are this is going to be give you the JP. So there is a nice form that we people write for JP that comes out to be x by 2 or p to sum. So minus 1 power m upon factorial m to gamma of m plus p plus 1 to x by 2 power 2m. Okay. So you can see that this is well defined even for complex numbers. Even if I take p, so far I have been talking only is p is a real number. So even one can take p belongs to a complex number. This is a completely different theory that continues from here with the real part of p is positive. So you can define these gamma functions. Okay. And you may ask the question that gamma of m plus p plus 1, if I what should I do for g minus p? Okay. So g minus p also becomes you can write the same thing. It becomes like this factorial m into gamma of m minus p plus 1. Okay. So when even this gamma function is well defined even for negative real numbers, they are not negative integers, the gamma function is well defined. So this is the you can use Ramanujan's theorems, or you can use the thing to define this thing. So any gamma function is defined for any complex number which is which are not negative reals, negative integers. So using that one can do, these are well defined, and therefore one can write this kind of functions, and these are called the Bessel functions generally. Okay, Bessel functions are the first kind, and Bessel function of the second kind, you take the very general solution, that is adding a series with the log x into the first solution. Therefore one can find the solutions of this type. So I will stop it here, the Bessel functions. If you have any questions, you can ask me before I go to the next topic. Next topic means subtopic of the series solutions. There are no questions?
So,
Sir, in the previous lecture, we have defined Bessel function of zero order for x is greater than 0. So why we have defined for x is greater than 0? Why that is not valid for
we are writing x by 2 power p, right? So if x is greater than 0 only, I can write any real number. P is any real number.
सर जब हमने j of minus p डिफाइन किया तो उसमें भी तो x by 2 की पावर minus p
Yeah, that's true. It will come x by 2 power minus p. It's the same thing. I'm just replacing p by minus p. Okay, so the next, so far what we saw is the solution of linear second order ODEs, right? So this we used very nicely the linearity to find two linearly independent solutions, to also to sum and subtract the series, infinite series. So the next question asked is what happens in case of nonlinear equations? We know many nonlinear equations, and we know the methods to solve nonlinear equations. Maybe you don't know how to solve the nonlinear second order equations, but I will tell you during the next discussion on the next topic. At least for the first order nonlinear equations, say for example, if I take y prime equals to y square, okay, and y at 0 is 1. We know how to solve this equation by separation of variables. Right. So, but now I am asking the question: what can't we write the series for this? Okay, so can't we write the series for this? If I write for the series expansion for this, Taylor series expansion, what happens to this? And what are the more general equations that can have the series solutions? So if I take this equation, then you see that I can write y0 is 1 and y prime at 0 is y square at 1, that is again 1, right? And y double prime at 0 is going to be 2y into y prime, okay? And y prime both are 0, therefore this becomes 2. So I can write what is the this one. So it is going to be 1 plus x square and so on. And this is the function. We know that 1 by 1 minus x. And we also know that this defines a solution. This is a solution of this initial value problem, right? So you can directly check this. Substitute in the equation, and then you see that y prime equals to y squared. So that means that I am getting a solution, and where the radius of convergence is less than 1. Okay. So therefore, this is a real analytic function, and it satisfies this equation. So of course, this requires the function, the right-hand side function should be able to differentiate as many times as possible. So the natural question is that if I take an equation y prime equals to, say, f of y, y prime equals to f of y with some initial condition. Say, for the simplicity, I take y at 0 equals to 0. Okay. Where f is a function of y. Okay. Fy can be y square, or fy can be exponential of y square, or fy can be 1 plus fy can be 1 plus cos y plus sin y, something like this. All these are all composition functions, right? So y prime of x is f of y of x. So for all these functions, can I do this series expansion? Yes, I can do the series expansion for this, because I know that y square has a series expansion. Exponential of y square also series expansion. Cos y is there, sin y is also there. So I can write the series expansions of these functions, and then I can write as many derivatives as I require. Right? As I require, I can write I can find all terms of the Taylor series for this equation. Therefore, I can call this. I can expect to have a series solution for this. So it is due to, again, Cauchy, and also there is another person, one of the great analysis person in those days, Kowalewski. So this is Cauchy-Kowalewski theory. So what the theorem says is that if you have a function f, which is from -1 to 1 to r, okay, be a real analytic function. Be a real analytic function in some neighborhood of 0. Let me write around 0. And you also know that ux is the unique solution of the equation u prime x is equals to f of x with u at 0 is to 0. Doesn't matter, this then u is a real analytic. So why I am assuming this the solution is already a solution is because for this type of equations, I will tell you next time, just after this topic. It's not really difficult to get the existence and uniqueness of the solutions using some little more analysis, using some metric spaces. One can show that the solutions of this equation always exists. Okay, and also they are going to be unique at times with a little stronger condition on F, which is which is actually a much weaker condition compared to real analytic. So all the real analytic functions if you have, then you always have a unique solution for this. Okay, so what the main point is that if there is a solution for this, this is going to be a real analytic solution. That is the that means that whatever the solution that you find, that is nothing but a real analytic solution. So we'll see how the real analytic solution for this problem will be there, or the UX that which is a solution is a real analytic solution. Is that clear what we are trying to prove? Or
Yes, sir.
Yes, sir.
So, or I'm going to write, when I write the series expansion, which is like this, okay, un0 by factorial n into x power n. We are going to show that this is actually a real analytic function, is real analytic. So this is, okay, so converges, and this is what our aim is.
Yes, sir.
Okay. So how this is done? So let us try to observe what are the coefficients that we have. So u prime equals to f of u, and u at 0 is 0. Okay. So this also tells me when I differentiate this, when I write this, actually gives us u prime 0, okay, is nothing but f of u at 0 is going to be 0. Right. Similarly, now write what is u double prime. This is going to be f prime u into u prime 0. Okay. So this is f prime u is f prime at 0. This is going to be u at 0 is 0. F prime at 0 into u prime 0 is going to be f at 0. Okay, at 0. Similarly, you can write a third derivative. The third derivative is going to be, now write this f prime, you have first term, if I differentiate, I get f double prime u into u prime. So u prime, already there is one u prime is there, square, plus f prime u into u double prime. Okay. F prime u into u double prime. So this is going to be, so f double prime at 0, this is going to be f double prime 0. Okay. U prime 0, right? So u prime 0, we already know that is nothing but f at 0. So this is f at 0 whole square, plus this is f prime of u, right? F prime of u at 0, that is again f prime at 0, times u double prime at 0 is nothing but f prime 0 into f at 0. So this is going to be simply square. So if I observe what these things look like, they're all this, each derivative is having the terms which are f0, f prime 0, f double prime 0, right? So I can write the nth derivative of this at 0, okay, is a polynomial of degree n in the n variables, in n variables. So on those n variables, I can write maybe those variables are going to be f0, f prime 0, and f n minus 1 0. Right. So how these polynomials look like? For example, look at u prime 0 is simply, right. So u prime 0, right. So is simply, this is something like x. This is like x, and this is f prime 0 is, if I write y, this is y into x, and this is going to be, we write x and y is chosen, y prime, x is f at 0, y is f prime 0. So, and z is f double prime. So this is z into x square, right, plus this is y prime into y square into x. So this is how this third polynomial looks like, right? So the third derivative is a polynomial in 3 variables, that is x, y, and z, and the order of the polynomial is 3. So UN0 is actually a polynomial, nth order polynomial in n variables. In n variables, okay, with positive integer coefficients. Positive integer coefficients. This is very important. You see that each of the polynomials what we wrote here, say first one is x and the second one is y into x and third one is this one. Why we are saying this is a polynomial is that this polynomial here doesn't depend on you, right? So this polynomial doesn't depend on you. It depends only on f at 0, f prime 0, fn minus 1 at 0. Okay, so these are the only variables. The un at 0 depends on only on these things, and each of them has a coefficient. All these polynomials has coefficients 1, 1, and maybe when you do the other one, fourth derivative of this, then you get maybe 2, like that. So they are going to be the coefficients which are positive integer coefficients. They are going to be positive integer coefficients. Why is that so important is I'll tell you what happens in case of positive integer coefficients is if I take P2 of xy. So what is the P2 of xy we saw here? P2 of xy is nothing but y into x. Right? So this is nothing but x into y. So when I take the absolute value of this, so this is simply mod xy, right, which is equals to mod x into mod y. So this is, in this case, it becomes P2 of mod x mod y. Okay. Similarly, look at what is P3, x, y, z. So this is, we wrote this as P3 as zx square plus y square x, right? So zx square plus y square x. So when we do this, this is going to be less than or equals to mod z into mod x square plus mod y square to mod x. So this is again P3 of mod x mod y mod z. So what is that we have from this is that this is happening because of the coefficients are positive. So I'm getting P3 of this. I'm just taking the modulus inside this polynomial, okay, and then writing this. So that is this Pn, okay, of f0, f prime 0.
सर इसमें साइन लेस देन इक्वल टू नहीं आएगा?
उस इसमें लेस देन और इक्वल टू आएगा ना, बिकॉज देयर इज अ प्लस हियर.
सर P3 के लिए जो लास्ट में लिखा है ना zx स्क्वायर प्लस y का
This is
स्क्वायर,
equal, right? These two are equal, no? This is nothing but P3 of mod x mod y mod z, right? That's what it is.
सेकंड टर्म तो इक्वल है, फर्स्ट से तो एक बड़ा ही होगा.
सर फर्स्ट टर्म
First term is equal, and from here apply the triangle inequality. From here to here apply the triangle inequality, mod a plus b less than or equals to mod a plus mod b, and that is P3 of mod x mod y mod z. I don't know what.
Yes, sir.
यस सर.
Yes sir, clear.
Right, so this is the polynomial. When I take the absolute value of this, okay, so this is less than or equals to the Pn of mod f0, okay, and mod fn minus 1 0. So what is happening is that when I take the absolute value on these Pn's, it is I can estimate them by taking this mod inside the variables. That's all, inside the polynomial. That is the this is happening because of positive integer coefficients. Okay, the coefficients are natural numbers. That is why this is happening. So this is one observation, first observation. And why we need that? because whatever we saw earlier, to show the convergence of the series, I am going to estimate them, right? Un, I want to majorize them by compare with another series which converges. So for that I have to write the mod un0 with taking the mod on this, and then I have to estimate this, right? So let us see how this estimation is done.
So can we do this same for positive real numbers?
Of course, yes, if it is positive, but we don't have in this case. But if there is a situation where you have this, then we can do it. It doesn't come in the PDEs of this type, naturally. Okay.
Sir, please,
so let us
once show the back slide. Yes, sir. Then why we should write because of positive integer coefficients? If it is not, then also true.
no, it is not. No?
Less or
Then it
equals
is not.
to.
See, I am writing the same Pn, right? So this is P3. I am also writing P3. If they are not positive, they are negative coefficient, negative integers, then I cannot write P3 here, right?
Okay, sir. Okay, sir. Okay, sir.
Yeah. Okay, so let us look at this one. So un at 0. Okay, how are we? When I write the absolute value of this is nothing but the mod Pn of whatever you have, that f0 and f prime 0, all those, right? So this is now we have the estimation. So that is, we have the estimate. This is now less than or equals to the Pn of mod f0, mod f prime 0, right? So we assume now a good assumption. Assume that there exists a real analytic function gt, which is real analytic, such that mod f n0, okay, is less than or equals to gn0. And second one is, when I take the equation v prime equals to g of v with v at 0 is 0, has real analytic solution. So this is an assumption. For the time being, this is an assumption. Once if we assume this, I'll show you why this is possible. Okay, once we assume this, then what happens to this Pn? Now I have mod fn0 less than or equals to gn0. Therefore, the polynomial is again with the positive coefficients. Positive coefficients. Therefore, this mod un0 now becomes less than or equals to, right? Becomes, now using this, it becomes mod un0 becomes less than or equals to Pn of g at 0, g prime at 0, gn minus 1 at 0. No mod g, like this. Okay, so this now again recall what we did. We had a problem like this. We had a problem like this, where f in place of g. Okay, where we had f in place of g. And when we computed the derivatives of v, we got this Pn of f0, g prime 0, and like this. So now if I look at what is this Pn of this is nothing but Vn0, right? That is coming from this assumption that this has a solution. So from that assumption, I see that Vn0 is exactly equals to this. That means I now majorized, or I compared this un0 by Vn0, where this Vn0 helps me to, actually this has a real analytic solution. Real analytic solution means the V can be written as Vn0 by factorial n into x power n. And therefore, this comparison gives that mod Un0 by factorial n is less than Vn0 by factorial n. And this is now this converges. Therefore, Un converges. Is that clear?
Yes,
Therefore,
Yes, sir. But we
Yes, sir.
therefore now my U becomes a real analytic function, or the series of U converges. Okay. So
sir,
now
but
this,
how can we say that कि every time this function exists, मतलब जो हम assume कर रहे हैं वो, how
I'm
can we
sure
say?
that once if you are convinced with this proof that U is a real analytic function, I will show that this assumption is not a big deal. We can assume this.
Okay, sir.
I'll show that this assumption why it comes, because I have not yet used the hypothesis. What is the hypothesis? Hypothesis is that F is a real analytic. I didn't use that yet. So if I use
Yes.
F is a real analytic, I will get this assumption. I will prove this, that the existence of G. Right?
Okay.
Is this clear? How we are proving this? We are proving this once if we have this G. Now I will use the property of the polynomial, that the polynomial has a positive coefficients. Okay, and this comparison, the comparison 1, gives me that this is going to be less than or equals to this. So this is the one. This gives this. Okay, and by the second assumption, we get this. Therefore, Un0 is less than or equals to Vn0, and V is a real analytic function. Therefore, the series of V converges. Therefore, the series of U also converges absolutely. Right. So let us see how this proof of existence of G. Proof of existence of G. So we know that F is a real analytic function. Therefore, F at t, okay, F at t, we can write this as F n0 by factorial n into t power n. So this is true for mod t, say less than r. And therefore, if I take t equals to r, t equals to say some rho which is less than r, then we have that these coefficients are bounded. This is what we have been using. Therefore, I can straight away use that. I can take C to be the maximum over n of mod 1 by factorial n of Fn0 into rho power. Take this as a maximum. Okay, so this implies that 1 by factorial n times mod Fn0 is less than or equals to C rho power minus n for all n. For all n. So this we have from the given assumption that F is a real analytic function. Now from here, let me write what is GT. So let GT be, I just simply take this one, that is the sum n equals to 0 to infinity C into T by rho power n. It's coming from this these numbers. And what is this this one? This is nothing but C into 1 minus 1 by x by rho. So this is nothing but C rho by rho minus x. Sorry, T.
Yeah.
So now I have the GT. GT is 0 by rho minus t. So if I take this GT, then it satisfies this assumption, the first one, that is, these are the GNs. These are the, if I from the power series we write this. So GNs or GN at 0 is nothing but 0 power minus n, and that is anyway compared with here. Therefore, I have the Fn. So for this one, this implies that Fn at sorry, not Fn. Yeah, from this comparison. What is that? Fn0 is less than or equals to Gn0. Yeah. So the first this implies that you have the first one, that is Fn0, okay, less than or equals to Gn0. Okay. That's how we constructed. We constructed that way only. We have taken Fn0 and then we took this one, this fellow from here, and then wrote the series, and we have this. Now the second assumption we have to show is that V prime. So we have to show that V prime equals to G of V. V prime equals to G of Vx. Okay, V at 0 is 0. That is has a solution. So y prime equals G prime V prime equals to 0 by rho minus V. You see that this is a nonlinear equation, right? So V at 0 is 0. But this equation is not difficult to solve. So if you write this equation, this becomes V into V prime minus rho into V prime plus 0 equals to 0. Okay. In other words, you can in the form of exact form half into the derivative of V square minus derivative of rho into V plus 0 equals to 0. So just integrate this, therefore we get the function Vx. Okay, so we get a quadratic equation V square, and therefore you can write Vx to be equals to rho minus, you get rho plus minus, but minus 2 rho into x. Okay, you get a quadratic equation that is V square minus rho V plus 0 equals to 0. So just write what is using the roots of that. You write Vx equals to rho plus minus, but the plus 1 doesn't satisfy the V at 0 is 0. So we take minus 1. And we know that this is going to be real analytic for mod x less than rho by 2, right? Mod x rho by c. 2c is also there. Yeah. So this is mod x less than rho by c, rho by 2c. So this is going to be a real analytic function. So that's what we assume, and therefore we have the result, a complete result. So next we will see that this kind of real analytic function, the real analytic solutions, we cannot actually find for equations like y prime equals to 1 plus root of mod y, if I have this, or even y prime equals to 1 plus y power 2 by 3 with y at 0 is 1, okay, or y at 0 is 0. So I cannot apply the series solution for this. So cannot find the series solutions because I cannot find the y third derivative of y. So series solution is not possible. It's not possible. You cannot write the series. But for solving a first order differential equation, once if you have a series solution means that you have an infinitely differentiable function. That is not required, right? So this is a first order equation, therefore the solution has to be only differentiable ones. So we'll see some methods based on this, how such kind of equations can be solved. Any other questions?